Hi, welcome to the second part of the QTI lecture series. Here I will be showing a tutorial of the QTI implementations in Dipy. This tutorial will follow the similar format of my last DKI and microstructure model tutorials. So I recommend you to give a look to this tutorial if you haven't done yet. Also, if you're at the moment only interested in knowing the theoretical part of advanced diffusionmri sequence, to make questions on the Q&A session later today. You can also skip the next this video and go to the next video where I will be explaining the theory of correlation tensor imaging to more generally extract kurtosis sources. So the tutorial of this talk can be found on my GitHub page. So GitHub Raphael NH. There you can just press the button repositories. The tutorial was prepared for and presented for the first time on the Dipy Workshop 2022, so you can press there. There you will find a notebook, so tutorials 001 QTI. So if you open it, you will see the following notebook. You can also download it to your computer and run the notebook locally. But if you just want to give a look to the code, you can just open it on the website. So if you scroll down, the first thing that you will see on the tutorial is just a theoretical explanation of how we are doing the QTI fit. So basically how we are linearize it to fit it using a weighted linear least squares. The complete information of this linearization can also be found on the original article by Westin et al. 2016. So if you scroll down the notebook, you will see the first code. So in the first lines of code, we are just importing the relevant models for this tutorial. And then you can just call the QTI reconstruction model using this command. So has the other reconstruction models for the single diffusion encoding. They are saved on Dipy reconst. So you can import QTI by writing import dipy.reconst.QTI has QTI, and then you're ready to use it. To input your data, you need to know the directories of your diffusion MRI data and the information to reconstruct the gradient tables. So not everyone has data from multidimensional encoding. So Dipy supplies a sample set of this type of data. So if you don't have this data and you want to try this tutorial, you can just use these command lines. So here I'm just uploading directly this file using this equation here. Well, you have to specify that is QT linear tensor encoding planar encoding file, and this function will upload the data and give the files, the directory of the files that were downloaded. So the first will contain the directory of the diffusion weighted images. It will contain a bval file that will show the magnitudes of each QTI experiment, the main directions of the tensors, and also will provide the directory of a mask. So you can use it to avoid calculations on the background of your image. So in the following lines, we're just loading the directories to a four-dimensional data. We are loading also the mask and reading the magnitudes of p-values in the directions of the B tensor. So as I explained, sometimes our scanners don't give the information of the full B matrix, but only the direction, the magnitude in this shape. So here we know the information of the shape a priori. So we are just saving an array saying that the order of our acquisitions is B0 acquisition. Then it's followed by 60 linear tensor encoding acquisitions and one B0 and another 60 directions for planar tensor encoding. So to automatically reconstruct the full B matrix, this will be done automatically on the gradient table object. So in opposite to the previous codes that you only need to give the B value in the B vector information for the acquisition. Here now you also have to input this array containing the shapes, and the Git tab will contain, will calculate and will return a Git tab that will have your B matrix computed. So here we are just checking that if these calculations were well done by looking to the ranks that were saved on GitHub B10s. And so if it's rank 1 is linear tensor encoding, and if it's rank 2 is planar tensor encoding. So we're basically checking that. And we see that indeed we have 60 volumes with linear tensor encoding and 60 volumes with planar tensor encoding. Okay, so now let's look at the next slide. So after you have your data loaded and save it to a matrix, and you also reconstructed the information of your acquisition and saved on the GitHub object. So the first thing that you have to do is just to define the QTI model based on the gradient table. So this will basically do all the calculations that are equal for voxel and voxel. And after you define the QTI model, you can just fit it by inputting your data saved on the 4D matrix and a mask, a 3D mask that indicates which are the voxels that should be processed. So this will do it all the processing for you. And then after having this object, then you can extract the different metrics from QTI. So in this case, we are just extracting the conventional FA of the diffusion tensor. Again, QTI also computes the diffusion tensor of DTI. So you have all the parametric metrics of DTI using this model. And here, so we are saving the FA map, and then one of the metrics that can only be computed by advanced diffusion encodings, which is the micro FA, and we are just saving it here. So in this block of code, we are just plotting the results for a given slice, and then you can see the comparison between the FA and the microscopic FA produced by this code. So moving on. So then the tutorial will finish with this large amount of lines of code. So basically what we are doing here is just plotting other measurements that this QTI can produce for you. And this is the given image. So here are the all other measurements that you can extract from it. And just to point out that, for example, K-ISO and K and ISO correspond to these two maps here. They have a slightly different name on the code because we are using a nomenclature by Westing et al. But basically, the key bulk and K shear corresponds to K ISO and K ISO. For the information of the other measurements, I will recommend you to give a look to the original manuscript. And given to time constraints, I will not have the time to explain everything. So just finally, I'm comparing our maps that we obtained using our code with the original manuscript. So yeah, so we can obtain all the measurements that Weston et al. Proposed. There's some, you can see that the contrast might look a little bit different, but this is basically because uh, we try to improve the quality of the acquisitions that relative to this preliminary work. So, for example, we are ensuring that we have all the enough data to fit all elements of the C tensor, the covariant tensor, but you can still see that both data have common aspects. So, for example, the K ISO values show hyper intensities on the boundaries between tissue and free water, which is the regions where you have the high variances between free water and tissue water. And for example, the K ISO maps, you see the high anisotropies on white matter, which is common to the high anisotropies observed on the original paper. And that is all for this tutorial. If you have any questions, feel free to contact us, or attending the Q&A session, or writing us on private. And thank you for your attention.